Thank you very much. It's great to be here. So many thanks for the invitation. It's fantastic and overly introduction. Very kind. So yeah, it's great. And let's look at the outline. What we're going to talk about. The first part is a set of fairly well-established methods at this point. So it's these ideas for how to use randomization to compute low-rank approximations to matrices, and it's well-established work at this point. Several of you have seen this many times, but it's really, I think, it's an unusual set of techniques in that you can actually explain them in a reasonably comprehensive way and you have broad appeal. So we decided to do this part, even though we actually did a version of it for the SIAM Pacific Northwest meeting 3 years ago. But the last part of the talk here about how these things apply for approximating continuum operators is perhaps new to more of you. So bear with me, those of you who have seen some of this stuff before. All right, so the basic problem we're going to address, it's a very classic standard problem. We're given a matrix, so you can think of it as being very large. It doesn't necessarily have to be super large. These methods still are highly competitive, even at smaller matrix sizes. But so you're given a matrix, you want to compute some low-rank approximation to it. And for now, we don't care so much exactly which format. Is it a QR? Is it a SVD, a partial SVD, or something like this? We just want to compute these factors, E and F. And this is, of course, data compression, that there's much less information in the factors than in the matrix. So how do you extract that smaller amount of data? And since this is applied math, I'm going to not spend a whole lot of time talking about why we care about these things. This is, of course, a standard problem in computational statistics. You want to fit a set of data points to a multivariate normal distribution. It's a very standard thing to do in all sorts of areas of computational science, where you do a reduced model of some linear system, and so on. And let me stress straight up for the people who have a familiarity with numerical linear algebra that the only thing I'm going to care about in these methods is to minimize the residual. So specifically, we're not talking about hard problems like finding the eigenvalues of a highly non-normal matrix or something like this. It's a basic low-rank approximation problem. All right, so to be precise, in introducing these ideas, I'm going to formulate this. So the more precise mathematical formulation is that I'm going to look for an approximate orthonormal basis for the column space of the matrix. So I want a set of vectors that approximately span the range in this sense. So that QQ star is the orthogonal projection onto these vectors. Right. So if you can solve this problem, then after that, any other specific low-rank approximation you want is very easily attainable. Just to illustrate, say that the matrix is symmetric and you want an eigenvalue decomposition. And if you have this basis, all you do is that you apply the orthogonal projection on both sides. You get the small matrix B, that's a projection of the larger one, and you just compute its eigenvalues, and you get a good approximation to the original matrix. Okay, so this is a very well-studied problem, obviously. There are lots of known algorithms for this. If the matrix is a reasonable size, say a few thousand or less, and you're doing this as a one-off computation, there's really nothing to say at all about this. You just load up whatever your favorite software package, you compute the full SVD of the matrix, and you take the dominant k left singular vectors. This is a very accurate and stable computation, and it solves the problem in an optimal way. The issue is that this is kind of expensive. So if you need to do this many, many times for moderate-sized matrices, or if you want to do it for very large matrices, then this is not viable. So another thing, a standard technique for large sparse matrices or some other matrices where you have a matrix vector multiply is to do some sort of Krylov method. So you take some starting vector, and then you look at the space obtained by applying powers of 8 to that vector. And then you look for your basis in that space. And that's oftentimes optimal. If the metric is number of matrix vector multiplies. So we're going to cycle back to Krylov method several times during the course of the talk, because that's sort of the main competition here. But in order to describe these ideas, our startup point is going to be something simpler than Krylov method. So we're going to start with just a Gram-Schmidt process, because this is the first thing we teach undergrads. Some people even do this in high school, that if you have a set of vectors, you want to build an orthonormal basis for them, the standard thing to do is Gram-Schmidt. So let's see how this works. So we think of the matrix as a collection of vectors. These are the columns of the matrix. And if we apply Gram-Schmidt to this, then you proceed, you all know this, you just normalize, you take the first vector, you normalize it, this is your first basis vector. Then you take the second column, you project it away from the one vector you already have, you normalize, now you have your first two, and then you proceed like this. Okay, so this can fail in many ways, right? That what if the first few vectors are linearly dependent? Then at some point you're going to hit a zero vector here. Or it could be that one of these vectors is very small, and in that case you lose numerical accuracy and so on. So the standard way around this is to not process the columns in order. Instead, you sort them by size. So you start with the largest one, the largest column, you normalize that, it gives you your Q1, you project away, and then you look at what's the largest survivor, you pick that one as the second one, and so on. And this solves the problem. So for all practical purposes, if you're willing to do this, it solves the problem. It can be stopped after k steps. It's a very robust technique. It can, in principle, be fairly suboptimal, but in practice, it really isn't. It works very well. Okay, but it is kind of expensive because it involves a lot of communication. But you really have to visit the entire matrix k times to build this basis. If the matrix is sparse to begin with, then typically you lose all sparsity very quickly. So it's not a particularly scalable method. But we can fix it by doing some randomized mixing of the vectors. So let's do Gram-Schmidt, but before we do it, we're going to form random linear combinations of the columns. So what we're going to do is that we're going to draw a set of random vectors from a Gaussian distribution. So what I mean there is that each entry is just drawn individually, independently from a standard normal distribution. And then I'm going to form the matrix vector products to get what I call sample vectors. So each vector yj is a linear combination of the columns of the matrix, so they all obviously sit inside the column space. And now the claim is if I just straightforwardly apply Gram-Schmidt to these vectors, so these all have the same distribution, so you can process them in any order, we just do them one at a time. Then this is going to solve the problem in many cases. And I'm going to make this precise. A simple mathematical analysis of this is as follows. So say that we have the exact singular value decomposition of the matrix. So this is just for purposes of analysis. Like this is it's not an algorithmic step. It's to understand what the method does. So we write A as the product of two unitary matrices, U and V, and then the diagonal in the middle. Okay, so now what is the expression we get for these samples? So I take the product V star times omega. Omega is from a Gaussian distribution. This is a rotational invariant distribution. So if I multiply it by a unitary matrix, I get another vector that's drawn from a Gaussian distribution. So this vector psi is also has a Gaussian distribution. So in other words, each one of these sample vectors, if we write it out, so I have these Gaussian vectors psi that multiply a diagonal matrix. So that's just diagonal scaling. And then they multiply the left singular vectors of the matrix. So remember at this point that the optimal answer is that I want to find the span of the first k left singular vectors, these ui's. That's the optimal answer. And what this formula tells you is that we're really biasing the sampling very heavily in favor of the top eigenvectors because they're weighted so that the weights here, this is a normal variable, normal random variable, and here we have the singular values. So the large ones get larger weights, the small ones that we don't want get smaller weights. So this is sort of a very simplistic explanation of why this works. And what is the cost here? It's to do the Gram-Schmidt has this cost, and then of course you need to form these matrix vector products, which has cost m and k. Okay, so we'll talk about in what sense this is better than other things you can do in a moment. But let's push through this analysis. So what does this mean? So let's think about a few different environments. So say A has exact rank k. Then you can show that with probability 1, these vectors are linearly independent. They all sit inside a k-dimensional subspace, so they automatically form a basis for the column space, so you're done. Like, this is an optimal answer. This algorithm just does it. So this is not typically what happens. Typically, you have singular values that decay. If they decay very fast, then you're almost in the exact right case. And you would expect this to perform very well, right? Because now we're very heavily favoring the top singular values. So the large sigmas, the vectors associated with the large singular values are now very heavily sampled. So we expect to do well. Conversely, if the singular values decay slowly like this, then we wouldn't expect this to perform particularly well, because each one of the samples is going to get a lot of contributions from the lower left singular vectors that we don't want to collect. And that's exactly what happens. And in that case, if you are in that environment, then you do need to do a little bit of powering of the matrix. So you get into a regime that some of you may recognize as subspace iteration, or we move a little bit in the direction of a Bloch-Krylov method in this regard. So what you're doing by taking your power of the matrix, so what I mean here is it's not that you're computing this power, it's that you draw the thin random matrix omega, and then you apply A to it to get another thin matrix, you apply A star, you apply A. So it's a succession of matrix vector multiplies, basically, with a small number of vectors. And the effect then is to just take a power of the singular values, which boosts the large ones. You increase the dynamic range between the components you want and the ones you don't want. Right. So let's look at some numerical experiments. So here we apply it to a matrix whose singular values decay very rapidly. The black line are the exact singular values. So this is the theoretically optimal. It's the best possible rank K approximation you can do. And this very simplistic method that I described gives the errors on the red line. So it's doing pretty well in this case where the singular values decay very fast. If you do powering in this case where the singular values decay rapidly, you're really killing the problem. It's sort of, at first glance, you get exactly the optimal errors, right? So, and this is exactly the type of matrices. I'll return toward in the second half of the talk. What is this kind of matrix? This turns out to be a scattering matrix in an electromagnetic scattering problem. And in this case, you have this fast exponential decay. So this is where we started using these randomized methods, and they just worked beautifully straight out of the book, much faster than anything else. And then, of course, we realized that, well, actually, there's a lot of people who are interested in low-rank approximation, and now we have this very fast tool. We should use it everywhere in data science, computational statistics, all this stuff. And then, of course, these guys, they typically have matrices whose spectra decay slowly, but there's a lot of noise in the data, and you have a weaker signal, and you want to pick out that weak signal. And in this case, the basic method performs quite poorly. If you do a little bit of powering, it performs okay. Okay? But you see, these are all like Jaggly. So there's a lot of randomness. If I ran, this is one instantiation, but the output is a random variable. So in order to try to explain this behavior mathematically, we have to use the language of probability theory, right? So we have to, the error analysis becomes probabilistic. So before one tries to prove anything, it's always a good idea to run some numerical experiments to form some idea in your head, what should you expect. If you run this, so this shows the outcome of 100 instantiations of the algorithm. And you see that they're very tightly clustered. There's not a whole lot of variance, which is a very nice property of a randomized algorithm. And the thicker line is the empirical average. So it's a very well-behaved method in this regard. It's tightly clustered, the outcome. If you're in this more challenging case, then it's a little bit worse. You have a little bit larger variance, but it still performs fairly well. And in particular, you basically never have a large outlier. So it turns out that if I had shown this figure for, instead of 100, I had done 100 million instantiations, you still would see no lines out here. But that you need mathematics to do, right? Because running this 100 million times would be very expensive. Okay, so this has been analyzed extremely carefully over the years. Let me just give you a flavor of the kind of mathematical ideas that come into this. So using deterministic methods, you can prove, so the error in this method, so the question is how good of a basis do the columns of Q form? How well aligned are they with the dominant K left singular values? So we look at the error here, and Eckhart-Young says that this error, it has to be at least this guy. So this is the norm of the tail singular values. It's a diagonal matrix that contains the tail singular values. So if this guy is large, we cannot expect to get smaller. We cannot possibly get smaller than that. And this term is a term that represents the suboptimality we're getting. If this term is large, then the algorithm performs poorly compared to the best possible outcome. And if this is small, then we're doing very well. So what's here? So here we have, again, the tail singular values. So notice in particular that the right-hand side does not depend at all on the top k singular values, which is kind of remarkable. And then we have this size, which are matrices that have Gaussian distribution of the dimensions given by the subscripts here. And the middle matrix here doesn't really impact much. It's just basically the norm of a Gaussian matrix. It's not going to move things much in either direction. What can impact things is this pseudo-inverse. So this dagger here implies the inverse if the matrix is square and a pseudo-inverse if it's not. So this is a rectangular matrix. So what I'm doing now is that I forgot to tell you, what I'm doing is I'm comparing the best possible rank k approximation to what happens if you draw L samples. Because we know when you're drawing samples, it's always a good idea to draw a few extra, right? If you don't, then you would have to be very optimistic to think that you're going to get a good result. So we compare the accuracy we get by drawing L samples to the best possible one with k vectors. And then we get this term. So this is the pseudo-inverse of a Gaussian matrix that's a little bit rectangular in this direction. The number of rows is k, and the number of columns is L. It's how many samples we take. Okay, so now one of the first things you pick up when you look at random matrices is if you have a square random matrix, then typically its smallest singular value is tiny. And it has it's very unstable. It can be extremely close to zero. It's expected to be fairly close to zero, and it can be extremely close to zero. So if you invert that matrix, you expect things to blow up. So if you don't do any oversampling, then you get very poor results. On the other hand, if you do a lot of oversampling, this is sort of in the first few weeks of your random matrix course, you learn about this Marchenko-Pasteur analysis, that's some sort of universality results that rectangular random matrices tend to be fairly well conditioned. So if you oversample a lot, then this term is going to be very well behaved, and that's what you would expect, right? So the interesting mathematical case, so now that we know about Marchenko-Pasteur, is what happens if it's almost rectangular. And here is the interesting fact, which is luckily for us, it was described very precisely just a couple of years before we did this analysis, that this turns out to be very well understood. What does the smallest singular value of an almost rectangular Gaussian matrix look like? And it turns out that it stabilizes extremely quickly. Just a little bit of oversampling really manages the situation. So I like to illustrate this with this graph. So what I'm showing on the y-axis, observe that this is logarithmic, is 1 over the smallest singular value. So basically, it is the norm of the pseudo-inverse. So the higher this value, the more suboptimal the algorithm is. So if you don't do any oversampling, then you have these red dots. So you see they're frequently orders of magnitude. So it's a terrible algorithm. It really doesn't perform well. But then this is the amount of oversampling. So the black dots, if you just draw 2 extra samples. So redly stabilized a lot. So the method starts to behave much better. If you draw 5 or 10 extra samples, you start to get almost deterministic outcomes. Like there's a little bit of wiggling around, but the likelihood of a large outlier becomes 0. Like I'm just talking about the expectation here, but there's analogous results about what's the likelihood of a large deviation. Okay, so then if you do the full analysis, you get this type of result that says that if you measure errors in the Frobenius norm, you're fairly close to optimal. If you measure in spectral norm, then you pay a large price because Eckart-Young tells you that this term is the optimal one, that you're paying the price of all the tail singular values. So it's underperforming by a lot. So this explains exactly why in the case of slow singular value decay, you don't get close to optimal results. And this is when you need to do powering. Right. So this is, let's incorporate the oversampling and we get the following algorithm. So you draw a few extra samples, typically 5 or 10 is sufficient. You do these steps that we already described. If you then want an SVD, you do the analog of the eigenvalue decomposition I showed on one of the first slides. You project your matrix down to the basis you constructed, and then you do a full SVD of the small matrix that you constructed. And these steps are just doing rotations within your construction. So this doesn't change the errors, really. Okay, so this is the randomized SVD, which is, has found a lot of use over the last several years. One important point here is, one reason that this works well is that you only need to, in the first step, it's a randomized step, but it can only fail in one way, and it's if you miss stuff. So many Monte Carlo style methods, they can fail in two ways, right? You can oversample and you can undersample. And you have to hit it just right, you need high quality, random numbers, and all this stuff. In this case, it's much simpler. You can be sort of brutal, you oversample a little bit aggressively. And you are going to collect some garbage. You are going to collect some contributions from the singular vectors you don't want. But this is where the second step becomes important because it filters that out. So the second step is deterministic, and it filters out the things that sort of entered unnecessarily from the oversampling. So it's a much more stable technique than most Monte Carlo techniques. Okay, this has been analyzed very carefully. We're still working on this problem. Let me skip this. And something that I'm not going to go into in great detail is that the analysis I just described, it expresses the error in quantities such as the exact singular values of the matrix. This is, of course, not known in advance, right? So it's not a useful, it's a useful theorem in terms of designing algorithms and understanding how they behave, but it's not useful in the sense of if you run this for a given matrix, what is the error? But you can do similar things to estimate what is the error. You can provide probabilistic bounds on the error using only quantities that you have at hand. So this is an active area of research. Right. So let's talk about the computational complexity here. So I mentioned briefly early on that the complexity here is MNK. So the dominant cost is this one. It's multiplying the matrix into a thin matrix with basically k columns and then the projection down. So there are two steps where you interact with the matrix. They both have complexity M and K. And this turns out to be the same as for the other methods. If I ran a Krylov method, I would need K matrix vector multiplies, again, complexity M and K. If I did column pivoted QR on the entire matrix, it would be K steps that each involved a rank 1 update. So again, complexity M and K. So we haven't beaten the standard methods in terms of asymptotic complexity, but it tends to be much, much faster because we spend all the flops in matrix-matrix multiplies, which are extremely fast. On the one hand, they're algorithms that don't require a lot of data movement inherently, and on top of that, they've been implemented extremely carefully. But hardware is really designed to do this fast. So this is why this is fast. And it's easy to code, right? So far, I assumed that K, the rank of the matrix, was an input. This is, of course, again, not typically the case. It's something you need to figure out. From a theoretical point of view, it's a simple problem. You just guess. You start guessing the rank is 2. If you have an error estimator, you see, no, that probably wasn't enough. Just double, keep doubling, and at some point you meet your tolerance, and you're done. It doesn't change the M and K scaling, but of course it is a bit wasteful. So what you can do instead is that you fix some block size, and you do a sequence of randomized SVDs of that fixed block size, so say 25. You process 25 vectors at a time, and you build your basis incrementally, like this. So this has all been worked out. It's very well understood how to run this in an adaptive mode. Right. And if you do this, it turns out you get very accurate approximations to the singular values on this middle factor, which also provides the stopping criterion for you. So these turn out to be the a posteriori error estimators, or this diagonal entries you get here. You can analyze this, and it works out beautifully. It's very precise, and it all works well. Okay, so let me just quickly mention, when I talked with the students, so I've been working on this low-rank approximation problem for well over 20 years now, and You know, I always think now this is completely done. There's nothing more to say about it, but then something happens, and this is the latest thing. So this is a preprint from just a few months ago, where it turns out so you can actually, using this, just the ideas I described, you can bring the complexity down to mn plus a lower order term. So how do you do this? So there's one extra assumption here. So this is not a completely black box algorithm. Here, I assume that I can extract rows and columns from the matrix, which in particular, if it's stored in memory, of course you can do this, but it's, or if it's a large sparse matrix, you can also do this. Okay, so what do you do? So you sort by fixing a small block size, 10 or 20 or something. You multiply the matrix together with a thin random matrix. So now you get a thin sample matrix with just, say, 10 or 20 columns. So it's not going to provide a basis for the column space. But what you use this sample for is that you find what are the dominant rows of the sample. And it turns out you can show that the largest rows of, so if you subselect k rows from the sample that form a good basis for the row space of the sample matrix, then those same k rows of the original matrix also form a good initial start of a basis for the row space of the original matrix. So I extract those rows, say 20 rows, and then I play the same game on the columns of the samples that I extracted, so I pick 20 columns. So now I get a rank 20 approximation to the matrix. So I use those rows and those columns, and I use those to form a rank 20 approximation to the matrix. The CUR approximation, if you follow these things. Okay, so now you implicitly subtract that from A, and now you play the same game on the residual. And you can do this by downdating the sample matrix you constructed in the first case. So you never need to go back and revisit the matrix. So you compute another sample from the column space of the residual. You pick 20 new rows, 20 new columns, and you play this game repeatedly. And this, it turns out, works very well. It is faster than the randomized SVD. It is adaptive. It is completely reliable because you can use these a posteriori error estimators. And yeah, I really don't know why it took us 20 years to figure this out, but it did. So yes, things are still happening in this field, even though one may not think it. Okay. Let me skip this. Let's revisit the algorithm and approach things from a slightly different side. Okay, so let's back up. So you remember at some point I used the approximation as q star times a. Okay, so what is q star? This is the orthogonal projection onto the sample that I formed. Okay, so I can express this instead of writing q star. I can express that as the sample matrix A omega. This is what I called Y before. Y times the pseudo-inverse of the sample matrix. Okay, so we have this expression for the approximation. So, right, well, this immediately leads to the idea, well, what if I do the same thing? Why am I approximating the columns? The matrix has columns and rows, so I pick one. So you could, of course, do it from the other direction. And then everything works, of course, analogously. But what happens if you do it from both sides? So then some interesting things happen. So if I use this approximation instead, so I gather samples from the row space. So I have my sample from the column space, and now I do the same thing with a matrix psi that looks like this. So I get samples from the row. So I use this as the approximation. This formula simplifies, so you can write it like this. Okay. Just repeating that formula. So now notice that something interesting happened, because I can collect these samples, this matrix and that matrix, I can form in a single pass over the matrix. So think of the matrix, there's a gigantic matrix that's stored on a hard drive, and you just need to, so in this case, right, reading things from drive is the expensive part. Flops are irrelevant in this context. Or you can think of it as an even larger matrix that you cannot store in a hard drive. It's just streaming past you. You cannot store it at all. But even so, as long as you get to see each entry of the matrix at least one, you can form this sample for the column space and this sample from the row space. And then once the matrix has streamed, it's long gone, you cannot revisit it. You can form this middle matrix and form this approximation, right? So now something very interesting happened because we found a streaming algorithm, a single view algorithm. And this you cannot do with deterministic methods, like Krylov method, column pivoted QR. They all require you to go back to the matrix several times. So this is something that's fundamentally different that randomization can do for you, that a deterministic one cannot. And this was something that was discovered early on in this work. Another interesting thing happens. Because now that we don't need to go back to the matrix, the question is, can we form these samples in a cheaper way? So can we, instead of using Gaussian matrices, use some simpler random matrices for which this matrix-matrix product requires less than m and k flops? But they're still random enough that they mix the columns and the rows sufficiently that all this works. And the answer to this turns out to be yes. Again, this was all discovered 20 years ago, that there are several different ways of doing this. My favorite at this point is to use a sparse matrix. So you can take these matrices omega and psi to be very sparse, mostly consisting of zeros. Just a small number of non-zero entries in each of the short directions. So for omega, the tall matrix, you draw, say, 5 non-zero entries in each row. That turns out to be sufficient for this to work very well. So you can now form the matrix-matrix multiplication in complexity mn, actually, and still do low-rank approximation. So now we did beat the traditional methods. So this is quite cool. And finally, just in case somebody is curious, I talked about a posteriori error estimation. This is probably a good point to mention. How do we do this in practice? Because when we use these more exotic random matrices, the underlying theory is much weaker. But these, in principle, could break. They just don't break in practice. In principle, you need something like k log k samples instead of k plus 10 samples. But it's extremely rare matrices for which this happens. But what you can do is you can rely on the Gaussian analysis not to build the approximation, but to estimate the error. So what we want to do here is that we draw a small random matrix that we keep quarantined from the rest of the computation. It's used only to estimate the error, and we can use something like a norm estimator like this. So we can apply the residual to the quarantined Gaussian matrix and get an estimate for the error. So as long as you're okay with dealing with the Frobenius norm error, this is fine. Spectral error estimation is a little more expensive. It can be done as well, but Frobenius norm is particularly simple. All right. Let's skip the linear maps. Let me say just a couple of words about randomized sampling methods. So these are techniques, the techniques I described so far, they rely on randomized mixing. So they're faster than traditional algorithms, but sort of not dramatically so. You can get the cost down to a few matrix vector multiplies, but it's not less than matrix vector multiplies. But in certain cases, you can do techniques, you can build methods that cost less than a matrix vector multiply. Of course, this cannot work in the general case, but in many specialized cases, this is of interest. So let's see, what's the idea here? So we think of a matrix as being built up of some simple building blocks. So for instance, you can take a sparse matrix and think of it as a sum over all its non-zero entries. You can take a general matrix and think of it as a sum of its columns. So each subpart here has only one column. You could do matrix-matrix multiplication. You can view the result, the factor here, the product, as a sum of rank 1 matrices. So the idea is to write the matrix in terms of some simple components, things that you can form very, very cheaply. Right. Now we want an estimate of the matrix. In order to do that, we put a probability distribution on your decomposition. And you can draw, in the simplest case, you can draw just one sample. And you boost this magnitude by 1 over the probability of drawing it. And then a very simple calculation shows that this is an unbiased estimator of the original matrix. That the expectation of this matrix X is A. Okay. So it's in some sense an approximation to the matrix, but it's a very stupid approximation, right? You take one entry of the matrix, for instance, and dramatically boost it. I mean, this is not useful. So in order to get useful things out of this, you rely on some sort of central limit theorem. You take lots of these samples and you average them. And the more samples you take, the more the result is going to converge towards your target. But convergence here is kind of slow, right? That this behaves exactly like Monte Carlo methods, that the error goes as 1 over square root of the number of samples. If you want scaling epsilon, you need 1 over epsilon squared samples. So all these methods have this nature, so they tend to be used not when you need very high accuracy, right? Unless you do some post-processing to it. But it's very useful in cases where you can't do other things. So if you have gigantic problem sizes, say you want to approximate a large tensor, and you're rotating over each of the dimensions, and you try to build a basis for each of the dimensions at a time, then in principle you need to solve a gigantic least squares problem, but that one can be very aggressively downsampled, and it still works very well. So here are some examples where this works. So these are all very large problems, but they don't consist of independent data. Like there are some correlations in the matrix that you exploit to do the downsampling. And let me just connect to, I understand that Joel Trop gave a talk about this last year. So this is a really cute hybrid method between sampling techniques and the mixing methods that I described before. So it turns out that for the specific task of doing a Cholesky factorization of a symmetric positive definite matrix, you can do this because you can use the diagonal entries of a positive definite matrix as the sampling probabilities. And in this way, you can compute a factorization in less than n squared operations, which is really cute. And again, it's in some sense surprising to me that these things are discovered. So I was not involved in this original work. We did some follow-up work, but again, the fact that it took so long before these things were fully described. And also, this is a very important idea. When you use sampling like this, you're going to get some samples that are very unhelpful. But it turns out that you can actually detect this and get rid of them to give very close to optimal algorithms. All right. So some of you will be bored at this point. You've seen most of this. Now let's talk about something that's perhaps less familiar. So do these ideas apply to large operators in scientific computing? So what I have in mind here are, so when we solve physical problems, we are oftentimes talking about global operators. You want to solve a PDE. So the operator I'm talking about here is the operator that maps boundary data to the solution in the interior, or body load to the solution in the interior. It could be various boundary-to-boundary operators, Dirichlet to Neumann, which are essential to domain decomposition methods. It could be that we want to understand time evolution operators. Okay, so can we apply these randomized ideas to continuum operators like this? So there are two complications here. One is that we now have continuum objects. You can, of course, discretize them to get matrices, but these matrices are very oversampled. So can we exploit the continuum nature in some way? And the other complication is that none of these operators are globally low rank. So you cannot apply this simplistic idea that I just described immediately. You have to do something a little bit more interesting. Right, so what I will do in the next 10, 15 minutes here is just to give you a very high-level vision I have about, so this has been my long-term vision. The randomized linear algebra has provided a diversion that lasted much longer than I had expected, but I'm really returning to this. I want to set up a framework where I can get data-sparse representations of these global operators of mathematical physics, and then do things like inverting them or forming linear systems where they form subcomponents and then inverting the resulting linear system. So the idea is really to get to a place in scientific computing where we don't need to rely on iterative solvers. And the advantage here are this will be particularly competitive in environments where we don't have good iterative solvers. So for instance, high-frequency scattering problems, which is something that we've done some interesting work on. Okay, so this is the high-level picture. This is going to be a fairly non-technical part of the talk. I just want to more describe the type of things we're interested in. So let me flesh out a little bit what I mean about the solution operators. So say we have a some elliptic boundary value problem. Think of Laplace or Helmholtz or something, right? The operator, so the standard paradigm for solving this, right, is you discretize using finite elements or something. You get a linear system, AX equal to B, with a sparse matrix, and then you solve that with an iteration. But really what the object you're trying to approximate is A inverse. So traditionally, we haven't tried to do that because A inverse is dense and A is sparse. Of course, you want to work with A instead. Let's say you could form A inverse. So my first argument is that this is mathematically much nicer. It's a much more tractable and benign problem. So let me illustrate. So let's look at a particularly simple elliptic PD. If you do just Poisson equation in free space, we can actually write down the solution like this. It's just a convolution with the fundamental solution of the PD, right? So in this case, solving the PD, there's no solution. It's just evaluating a formula. I need to evaluate the convolution between the data and a known fundamental solution. So mathematically, this is straightforward. Computationally, it's tricky, right? Because if I discretize this, I end up with a dense matrix that every point where G, I sample G at some collocation points or something, and I want to evaluate U, and all these points talk to each other. But there's this fast multiple method that does this in linear complexity. But this is one of the inspirations for what we want to do. Okay, so for all linear elliptic PDEs, there's some solution operator of this form. So these are integral operators, and they are nice. They are smoothing operators, so they're much more benign than the differentiation operators, which are unbounded and so on. So I'm arguing that this is a better post-mathematical problem, trying to build an approximation to this solution operator. But the tricky part, right, is that the kernels in these solution operators, they depend on the geometry. If you have variable coefficient PDEs, they depend on the coefficients. So this has to be done numerically, and we have to do something that exploits inherent structure in these operators to avoid the quadratic or even cubic costs that would be incurred otherwise. And the idea here is that these are Calderon-Sigmund operators. They are singular integral operators that have this property that's parts of the domain that are far away from each other. They all talk to each other, but the amount of information that gets passed is not very large. So linear algebraically, what that means is that you can tessellate this matrix that arises upon discretizing such an operator, and you get a matrix whose off-diagonal blocks have low numerical rank. And it turns out that the amount of information in such a matrix to any finite precision scales linearly with problem size, or n log n, or something like this. So I should say this is a cartoon. Typically, you have more complicated tessellation patterns because the tessellation is really based on a hierarchical tessellation of underlying space. So if you're in 3 dimensions, you have an octree, and the underlying, this is sort of the 2D, you're mapping, in this case, it's a 2D problem, it's a quad tree that's mapped onto some linear ordering of the matrix, right? So you really should think of these operators as tensors. They map 2 or 3 tensors to 2 or 3 tensors. But they have this hierarchical structure. Another one of these global operators that's very useful in scientific computing are boundary integral operators. So say you're looking at a scattering problem. You have some wave that comes in and hits an object, and it gets reflected something outgoing. You want to compute the outgoing wave given the incoming wave. So this is a fundamental component in radar, in sonar, in lots of imaging problems, medical imaging and so on. And it just occurs to me that I should, of course, have swapped out this for... When did Boeing last build a fighter plane? They participated in the 22, right? Okay, now I should know this. Okay, in any case, they have participated. Yeah, I think F-22 was in part built by Boeing. Okay, think of this as an F-22. It's a Swedish one. It's what I actually picked, but it's an old slide. Okay, so the point being that you can take this PDE that's written in the exterior of this domain, and you could instead write it as an equation that lives just on the surface of the aircraft, or whatever the scattering object is. So you can go from a PDE formulation in 3 dimensions to an integral equation that lives in 2 dimensions. And this is also much more benign formulation. But when you discretize this, you get a dense matrix. But it has this rank structure that we're going to exploit. All right, so this is another example of the type of global operators I'm interested in. I mentioned earlier the Dirichlet-von-Neumann maps. So if you take, say, a boundary value problem with Dirichlet data, if it's well posed, you can solve it. Then you compute the tractions. And the map that takes the Dirichlet data and maps it to the Neumann data is one of these singular integral operators. So this is another object that I'm interested in. Why should you care about this operator? Well, this is actually really fundamental in many parts of scientific computing. It encodes all the interior information about an object from the point of view of its interaction with the outside walls. If you want to do inverse scattering, you want to reconstruct the object, all the information that you can access from an imaging problem is encoded in the DTN map. In domain decomposition, it's the DTN map that you use to glue subdomains together. So the idea here is that you have some really large PDE. It's too large to solve on your workstation, but you have 100 workstations. You split up the domain in 100 subpieces. You let solve locally on each piece. But then how do you get them all to agree that they have the correct solution? And you have to enforce continuity conditions at the interfaces. And this is done through the DTN map. So in current scientific computing, it's done iteratively. It's done implicitly. You don't actually explicitly form the DTNs. They're just used to inform how do you build preconditioners for this. So here's a larger system with 6 subdomains. And you can form a global system for gluing these together that involve pieces of the DTN operators. Okay. So my vision here is I want to do this explicitly. I want to build explicit matrices for all these guys. You can do multi-physics problems or multi-discretization problems. Say you have this scattering problem, but you have a domain not with a hard surface that the wave doesn't penetrate, but instead you have some soft material, so the wave goes in. So this would be more the environment of medical imaging, right? So you have variable wave speed inside, and you want to reconstruct it. Now, how do you solve this? You have an unbounded domain with constant coefficients out here, so you should use the boundary integral equation. But then on the inside, you have variable coefficients, so you need to use something like a finite element method. So how do you get them to talk to each other? The DTN map. You build the DTN for the interior, the DTN for the exterior, and that gives you a way of gluing these things together. Or to be precise, you should actually, in this case, use the impedance to impedance, which is the Cayley transform of the DTN. So there are lots of things that I'm pushing under the carpet here, right? But these are really fundamental objects. Let's skip this example. In large sparse direct solvers, this also comes up sort of a little bit indirectly. And so say you discretize a PD, you get a large sparse matrix, and I want to compute its LU factorization. Well, you can again use this domain decomposition idea. I take the domain, I split it into 2 halves, and then if I can do an LU factorization of each of the 2 halves, I can glue them together through a Schur complement that lives on the interface. Okay, so here I did the formula for inverses rather than LU, but it's the same type of idea. So if I can do domain divide and conquer here, you split the domain into halves, so half the size. If I can solve the 2 halves, then I can glue them together under the assumption that I can invert this matrix that lives on the interface, which is a Schur complement. And it turns out that this Schur complement is a discrete equivalent of the DTN operator. Yeah, I'm trying to convince you here that DTNs and its cousins are really essential. So if you exploit this, you can actually do this, the inversion of this last step in linear complexity, and get linear complexity for LU factorization. And this is part of the big strategy here. This has all been done. For 2D, it works beautifully. We have wonderful codes. In 3D, it's solved in principle, but it's been really hard to get it to tie the bag on this from a practical point of view. And I'll tell you how to do it. Let's skip this part. Let me just say one word. Why do you have these rank decay? It's really because there's not much information that gets transported over distances. But if you do imaging, no information that's smaller than on length scales that are smaller than the wavelength propagates. They decay exponentially fast. It's that reason. It's if you work in elasticity, you know that if you take a solid body and you put a load on it, then if you look at the deformation some distance away, the fine scale of the load doesn't matter. It's just the total load and maybe a moment or something like this. So this is really the underlying. But that's how a physicist would explain it. A mathematician would start talking about, Calderon-Sigmund theory and so on. But it's really the same type of thing. Okay, so just the punchline. Let's do this. Okay, so how do you build these approximations? This is a problem that I've spent a lot of my time on the last few years. So we have this type of environment. So we can query some operators. So think of this as a solution operator to an elliptic PDE, as a DTN map, and you can do the matrix vector multiply. So in this context, applying the DTN map corresponds to solving the PDE. So the assumption here is that I have some legacy PDE solver. So I can query the operator. And then I want to pick some inputs such that I observe the outputs. And then the question is, can I reconstruct the entire matrix? So for the randomized SVD that we started with, it fits in this framework. And here's what the solution looks like. So it's a generalization of the framework we started with. It's just we'll go beyond low rank. And it's exactly what we talked about several of these examples. So it might be that you have a boundary integral equation. You want to directly invert its discretization because for these scattering problems, iterative methods work very poorly. You want to do fast direct solvers. So in that case, the matrix you're building is the Schur complement, which you can apply by having factorizations of the subproblem, and so on. We just want an explicit data sparse representation of these dense matrices. And this, it turns out, can be done. It was actually quite a long time ago that it was solved in principle. So Lei-Ching Ying and co-workers did some essential work in this direction for a very general class of matrices. So that showed that it's possible to do it in linear complexity. The prefactors were terrible, and it's been taking us 15 years to reduce the prefactors. We're finally getting to the point where these are actually becoming practical tools. And you had to really pay attention to numerical stability here. These algorithms are complicated. It's very easy to lose a little bit of accuracy in every step, and it all adds up. So doing it in a numerically stable way is very important. And then we also discovered shortcuts that there are. Sometimes you don't need these very general techniques. You can use simplified formats, which is with Heather's group. We talked about one of them in detail this morning, these HSS matrices and their close allies. For them, this randomized compression technique is really highly efficient. And one of my students worked out just a couple of years ago about how to do this in a fully black box way, which that was amazing to me. I had thought about this problem for 15 years, and I had not done it. And my student did it. We talked about this in the SIAM meeting. So this is what I referred to at the time. But so now we have these tools. We're finally starting to get the tools together. That's hopefully the vision here of doing direct solvers can be realized. And I should save a little bit of time for questions. So let me skip the technical discussion. It's the end of the day. Just a quick summary. So we started by talking about low rank approximation. And again, let me regret, some of you have seen this stuff before, but I think it's really quite cute because it's not relying on a small number of simple ideas. And a lot of these things you can code up quite simply by yourself. So it's easy to play with these things. And many of these things we did were discovered experimentally. It's so easy to set up these experiments. How much randomization do you need to get things to work? And you have something that you can pretty easily convince yourself is correct in expectation. And then the question is, how large is the variance? And you run some experiments and you see, well, the variance is tiny. And then you try to explain it. And some of the key things, really the basic randomized SVD I showed you first is the most commonly used of these by far. And the main benefit there is it has the same theoretical profile as classical method. It just executes faster in practice because it involves less data movement. But there are also all these fun theoretical things. You can do streaming algorithms, you can do complexity that's basically linear in the number of non-zero entries, and so on. We're currently working on the extension of these to tensors. This is a very active area of research. It's a very diverse research area because there are so many different environments to think about. We briefly talked about sampling problems, and then at the end, this like long-term pie in the sky goal of mine of getting rid of iterative solvers in scientific computing. And I should say, but both the good part and the bad part about that is it is everything I described, I know how to do in 2D. We can do it all. And it went pretty quickly that we managed to do all these things. But of course, these days, 2D problems are so fast to solve using any method, basically, that it's hard to really make an impact. And then the extension to 3D has been more challenging than I had hoped 10, 15 years ago, but I think we're finally getting there. So thank you very much.
Going back to the iterative CUR,
Mm-hmm.
so you end up kind of repeating on the residual. Do you see other algorithms where this idea can be helpful? Or is it kind of particular to the structure of that?
So that idea was used before. It's very similar to, so I started, one of the first things I talked about was column pivoted QR. And I said that the complexity, the main difficulty there is that each step of column pivoted QR, you need to revisit the entire matrix. You pick a pivot, and then you project the entire matrix away. So it's a sequence of rank 1 updates. So it turns out that you can use the randomized techniques to pick pivots. So it's the start of iterative CUR comes from that work. So you pick some block size, say 25 or something, and you extract, say you want to pick columns, in that case you extract a sample from the row space. So 25 random linear combinations of the rows. And then you do pivoting on those guys. And it turns out that the pivots you select are also good pivots for the original matrix. It's really fun. In cases where the singular values decay rapidly, you pick the same pivots. If they decay very slowly, you pick completely different pivots, but in that case, it doesn't matter. And the two extremal cases interpolate perfectly. So you always perform well, whether the singular values decay slowly or not. And so I hadn't made that discovery, that you could use randomization to pick groups of pivots in column pivoted QR and convert it into an algorithm that's dominated by BLAST3. So all the flops are in matrix-matrix multiplication. And then Minggu discovered that you can downdate the sample. So you only need to do that's one extraction of a small sample. So you get a sample of the rows, and then once you do your first step of the approximation, you can just downdate the sample you already collected. So in some sense, we already knew that you can do this. I just didn't make the connection that if you combine that with the CUR idea that if I have columns, then I can actually also pick rows. And if I do that, I don't need to revisit the matrix at all. So it was half these things. The students asked me if there were things that I had, mistakes I had made, like, well, what are things you wish you had done differently, or some problems you gave up on that you didn't think about? This would be one of them. You were halfway to the solution of, but just didn't think of it at the time.
Other questions? I have a broad question. You don't have to go into all the details. I'm just curious. So when you are thinking about extending to the tensor case, is there a particular unfolding or tensor-based decomposition that you find is especially useful, or are you kind of exploring more broadly all the different variants? Sorry, yeah.
Yeah, So the tensor case is curious, right? Because it's so rich. It's for a 3-tensor, many of the techniques that apply to matrices have a pretty straightforward characterization. Whereas if you had a tensor of dimension 20, it completely doesn't apply. So what I've been looking at is really the extension to 3 and possibly 4 tensors. Okay. So the immediate generalization of many of the ideas that I described here. And
I guess is it you like plug into matrices, or are you sort of looking at doing like the CP decomposition and using randomization in that sense?
Yes and yes. We do both.
Okay. Both.
And this is part of what's so frustrating about tensors, because there are so many cases that sometimes what you want to do is you want to take a couple of directions and unfold them to a large matrix and then use some sampling. Tammy Kolda pioneered these ideas, and it's a great idea. They're rich. You can use specialized random structures in that case, where you use Kronecker products as your randomization techniques, so you can compute these samples. But sometimes we find what we want to do instead is use random projections on several of the dimensions at one time. You crunch them down. And if you have 4 tensors, sometimes you want to do 2 directions you crunch down and you matricize one. And it's a whole zoo. But the good part is there are plenty of papers to write. But at this point, I don't have a unified framework that, what you should do generally for 3 and 4 tensors is such and such. But we're working on it. With luck, I'll have a better answer in 5 years, but it's entirely possible that the answer will still be. It really depends on how many dimensions you have, how large are they, what's the decay, and several different notions of rank, and do you care about the CP rank or Tucker, or we talked about tensor trains earlier today. And, there are lots of different representations here. And yeah, it's a much messier area than linear algebra. Yeah.
Okay, other questions? Anybody? All right, in that case,